No? A little bit louder. Okay. So I want to start just with very well-known background material. I'm going to talk a little bit about positive definite matrices. And in about 6 or 7 minutes time, we will have proved not the Hadamard conjecture, but Hadamard's determinant theorem, right? Hadamard's determinant bound. So for an n by n invertible matrix G, maybe over the complex numbers, or maybe if you really want to work with real Hadamard matrices over the reals or the rationals or something, the following are equivalent. So my matrix is of the form M conjugate transpose times M, or I can write my matrix as a gram matrix, meaning it's the inner products of a collection of n non-zero vectors. And either of those things is really a definition as opposed to a proposition. I'm going to call positive definite. And as I say, for me in this talk, Hadamard matrix will mostly just mean complex Hadamard matrix or generalized complex Hadamard matrix, however you happen to think about it. I would say real Hadamard if I mean something about real matrices, but not consistently. So we'll always be working over an inner product space, and I'll always use the standard inner product. And you can think about everything geometrically now, right? In the case of a positive definite matrix, because you can think in terms of the n vectors. And then the Cauchy-Schwarz inequality, which is written up on the board there, is exactly equivalent to saying that the principal 2x2 minors of your positive definite matrix are always positive. And what we can do now is talk about a little bit about Sylvester's criterion, which generalizes this. Sylvester says that actually a matrix is positive definite if and only if all of the leading principal minors are positive definite. So that means the top left 1x1 submatrix, the top left 2x2 submatrix, and all the way down. Because positive definiteness, where do I point? Do I point at the laptop? I point at the laptop. So positive definiteness is invariant under simultaneous permutation of rows and columns. This means that it's equivalent to saying that all of the principal minors are positive. And you should really think of this as a higher dimensional analog of Cauchy-Schwarz, right? So what I'm going to do now is I'm going to show you a simple corollary of this kind of geometric idea. And we're going to need this on the next slide. This is the only thing that I'm going to ask you to remember from one slide to the next. So if I have a positive definite matrix, then the determinant of that matrix is bounded above by the product of the determinant of the largest k-1 by k-1 minor times the other element on the diagonal. How do we prove that? Well, you use the fact that your determinant is linear in rows. This matrix has determinant gkk times, well, the principal minor. And this matrix over here, we have to think about a little bit, and we have to look at what we did on the previous slide, right? If this matrix had all of its principal minors positive, the matrix would be positive definite, right? And I can see that the first k-1 minors are all positive, because that's my hypothesis, that the matrix over here is positive definite. So if the determinant of this matrix, the largest minor, was positive, the matrix would be positive definite, right? And if it was positive definite, all the 2x2 minors would be positive. But you look at this bottom left guy, bottom right guy, the 2x2 determinant, we can all do this in our heads. It's negative. This is a contradiction. So this matrix has negative determinant, or at least non-positive determinant. And that's my bound, right? So I can say that the determinant of this matrix here is at most the determinant of this matrix. Well, because this thing is non-positive. All right. Is everybody happy with that? All right. Now, you remember this statement when we go to the next page, because we're going to prove Fisher's inequality, which is a generalization of that. Fisher's inequality says that I can take a positive definite matrix G, I can divide it into a k by k matrix in the top left and n minus k by n minus k matrix in the bottom right. And the determinant of G is at most the product of the determinants of the diagonal pieces, right? So we had on the previous slide the case that one of the pieces was n minus 1 by n minus 1 and the other piece was 1 by 1. So this is a generalization, right? How do we prove it? Well, the original proof, which is not what a numerical analyst would tell you, is the following. Just like Rob earlier on, you look at the kth compound of your matrix. So you take the n choose k by n choose k matrix, whose entries are the k by k minors of the original matrix, right? And I'm going to order my rows and columns so that the determinant of A shows up in the bottom right. And all of the other guys are inside of this matrix F. right? Now we skip some well-known details in the style of like Hadamard or anyone else from the 19th century. And I can tell you that, well, first of all, I should say, remember the fact from the previous slide. For a positive definite matrix, the determinant of the matrix is bounded by the determinant of the n-1 by n-1 minor times the determinant of the thing in the bottom right. That's what we're going to use. So I claim that the determinant of the piece that I called F is whatever this is, and the determinant of the matrix as a whole is whatever that is. And then you just put those things together, cancel out some giant common factor, and this is Fisher's inequality. And the well-known facts that we're omitting all have names associated with them, with people like Sylvester, Cauchy Binet, Jacobi, people like this. If you look in Horn and Johnson matrix analysis, there's a list of things like this about compound matrices that you should know. So that's the proof of Fisher's inequality. And it says we can always analyze, or we can always bound the determinant of a positive definite matrix in terms of determinants that show up along its diagonal. What has this to do with Hadamard? Well, here's the usual Hadamard inequality, or something that's closely related. If my matrix is positive definite, I claim that det G is bounded by the product of the diagonal entries. So what are you going to do? However you like, start with your gram matrix, break it into two pieces. We said that the determinant of the matrix as a whole is bounded by the determinant of the pieces along the diagonal. And then go recursively, right? Break each of those pieces up in two and so on, and keep going until all you have left are 1-by-1 matrices down the diagonal. That's a completely satisfactory proof of Hadamard's theorem. And I mean, historically, it goes the other way around. Fisher generalized Hadamard. But this is kind of useful, and you may want to use Fisher later on. He did, and he proved it by induction. Yeah. So yeah, but this was kind of controversial at the time. If you look at some of these, like Muir's history of determinants, Muir says that Hadamard proved this by mathematical induction, which he did not accept was valid. So he gave loads of different proofs over 30 years. So yeah, I mean, Hadamard's proof, I agree. Hadamard's proof is also fantastic, but you know, this was fun. So how do we get from this statement to the usual Hadamard determinant inequality, right? What do you do? Well, Hadamard is always comparing the, well, when you define a Hadamard matrix, all of the entries have norm bounded by 1. So I'm going to impose that condition. If I have a vector of length n, all of its entries are bounded by 1, then the diagonal entries in the gram matrix are going to be n, right? So what does Hadamard say? Hadamard says if all of the entries in my matrix have norm 1, then all of the entries along the diagonal in the gram matrix are at most n. So the determinant of the gram matrix is at most the product of the diagonal entries, which is n to the n, and determinants are multiplicative. So I pull that apart, and here is Hadamard's maximal determinant theorem, Hadamard's maximal determinant inequality, whatever. And just from the way that we worked through the proof, I mean, I guess I wasn't entirely explicit in all of the details along the way, but it's kind of clear if you think about what we did along the way. The only way that you could meet this bound with equality is if all of the entries in each of your vectors have norm 1, and if each pair of the vectors are orthogonal. All right. So at this conference, nice to see a proof of Hadamard's inequality at least once. And that tells you essentially what you're going to try to achieve when you build a Hadamard matrix. So you're looking for n vectors, which are pairwise orthogonal, and all of the entries should have modulus 1. Ah, that's what I said. So over the real field, your entries of modulus 1 are kind of restricted. All you have are plus and minus 1s. And it's not so hard to see that you can build Hadamard matrices in dimensions 1, 2, 4, 8, 12, and so on. We know that you can't build 3 pairwise orthogonal vectors if the dimension is 2 mod 4, but otherwise we don't know of any restrictions. People have looked quite hard for restrictions, and so the Hadamard conjecture is that for every multiple of 4, every dimension that is a multiple of 4, you should be able to build a Hadamard matrix. Over the kth roots of unity, you can ask exactly the same question. And we know how to build some matrices. The classical examples already found in Sylvester are the character tables of abelian groups, but there are lots more, and we'll come back and talk about complex matrices later on. And I suggest that you should ask, well, you could ask for any set of entries in the complex numbers which are of norm 1 or at most 1, we can write dne for the maximal determinant of an MN matrix with entries in E. Okay? Then we have a Hadamard conjecture. When can you achieve the Hadamard bound? I mean, that should be associated with some sort of like, list of integers or something like that. But there's also this idea of a Hadamard bound, which is what I want to talk about a little bit more. And the question now is, well, we know sometimes we can achieve the bound and sometimes we can't. But are there constants of some sort which we can apply on the left or on the right? So in other words, if I can't achieve the Hadamard bound, can I say, well, you can't get too close to the Hadamard bound? And I'll show you exactly what I mean on the next slide. And we're quite good at playing this game on the right-hand side. So for various, at least in the real case, I can give you fairly precise answers for what these constants C should be. On the left-hand side, we have more progress to make. So I'll show you what's known about this as well. So that'll be the second half of the talk. But the idea is that you can measure kind of quantitatively how close you are to achieving the Hadamard bound, even when it's not precisely achievable. Oh, I probably did. Oh yeah, square the inside, take square roots on the outside, but yes. Otherwise, those would be extremely large polynomials, right? But yeah, thank you. Yeah, that's a typo. Okay, so I just want to show you what happens, for example, in the case that n is 2 mod 4. So we know that, well, if n is greater than 2, so start with 6 or 10 or something like that, the Hadamard bound is not achievable. So I know that I can write down pairs of vectors which are orthogonal, but I can't write down triples which are orthogonal. So what do? You think about a graph, which you write down. This is kind of sketchy as well. Where we go. So I join two vertices. So the vertices in the graph are labeled by the rows of my matrix. And I connect two of these guys if the rows are orthogonal. And then because I'm in dimension, which is 2 mod 4, I know that my graph is triangle free. For some reason, I'd like to maximize the number of zeros in my graph. And by Turan's theorem, the largest thing that you could find is a complete bipartite graph. And you kind of play along with this game. You believe me for now that this is a sensible thing to write down and say, I want to compute the determinant of this gram matrix. And that's not such a difficult exercise. And if you can find two circulant matrices A and B which satisfy these equations here, then it's not hard to see that you can actually achieve this gram matrix. And you have to do a little bit more work to see that this really is the best that you could do. It's not terribly difficult. This is like maybe one page of a proof to come up with this as the optimal gram matrix. So the gram matrix is the largest determinant, and to decide as well that these are the sorts of things that you should try and build. So these are what this is exactly what the analog of the Hadamard conjecture should be when you're looking at n congruent to 2 mod 4. This is the gram matrix that you want to achieve. We can work out its determinant. We can say everything about it. So how does the upper bound look like in the real case? Well, if n is 0 mod 4, then the Hadamard conjecture is that always you can achieve the Hadamard bound. And we know that this is true up to, some reasonably large number like 600 and something. And we know that it's most of the time true up to even some larger bound. But beyond that, we run into trouble. I'll talk a little bit more about the density of the orders where we know that the Hadamard conjecture is true in a second. If n is 1 mod 4, then, so an argument which Guillermo will present in a bit more detail later on, will show you that the gram matrix, the type of gram matrix that you're looking for is this guy, which has 1s off the diagonal everywhere. And it's clear that you couldn't do any better than that because you can't have pairs of orthogonal rows when the dimension is odd. So you have something that looks like this. And you can work out explicitly what the determinant of this matrix is. And it's about 85% of the Hadamard bound. And these things are at least sometimes achievable in the sense that Brouwer has constructed an infinite family of symmetric designs that saturate this bound whenever n is of this funny form, like q squared plus q plus 1 squared. For q an odd prime power. There we go. So for n is 2, which is the case that we just looked at, you've got this, not awful looking gram matrix, and you can try and achieve these things. And again, you can compute its determinant. You see that this time you get about 73% of the Hadamard bound, but it's at least pretty close to the Hadamard bound when you can build one of these things. And there are some restrictions, number theoretic restrictions, and this bound can be achieved twice. Once if you double the construction that Brouwer had. So if you remember, Brouwer is constructing something that satisfies ones off the diagonal. You take 2 copies of that and you get matrices with 2s off the diagonal, which is exactly what you want to shove into your Gram matrix here. Join them together, all as well. There's also a second family, which were constructed by Spence using like projective planes and bare subplanes and things like that. And we get to the case 3 mod 4, where things are a little bit different. Unfortunately, in the 3 mod 4 case, we don't know what the optimal Gram matrix would be. Both of the first, like the n is congruent to 1 mod 4, the n is congruent to 2 mod 4. The analysis takes a page, more or less. The construction, Brouwer's construction is a little bit tricky. It takes 2 pages. And this one also is 3 or 4 pages. But for n is 3 mod 4, there's a paper by Alick, which is about 30 pages long. And he does some fairly detailed analysis of what the Gram matrices would be here. The proofs are long and complicated. But he comes up with a Gram matrix, which we know that we can't achieve most of the time, but he gives us something which is, smaller determinant than the Hadamard matrix. And he says anything that you can find will be smaller than this. So it's less satisfactory than the other cases. And we don't know that Alick's bound is ever attained, but we know that we can get to about half of the bound. And this happens quite often. And if you'd like to read more about this, Ronan, who's here, and then Patrick Brown and Fintan Hegarty, there should be a comment there. Those are 2 people. And myself wrote this survey paper last year, and it discusses all of this. So yeah, that's how far the survey paper goes, but I want to go a little bit further. So I want to just, I'm going to survey this first and then we'll go on. So in the real case, I said that for these like Hadamard maximal determinant problems, you should look at how close you can get to the Hadamard bound. And this table kind of summarizes what we know in the real case. So we can achieve the Hadamard bound quite often in the real case. So this is something I'll talk about a little bit later. This is work of Rob Cragen and his student from about 10 years ago. In the case that n is 1 mod 4, we can't achieve the Hadamard bound, but we can get reasonably close, and we can get reasonably close quite often. So we have a family, basically of order p squared, and the gaps between primes are what control the distance between these orders where we can construct these matrices. Same thing happens in dimension 2 mod 4. For dimension 3 mod 4, we don't know whether the Alick bound is ever achieved, but we can get reasonably close to it. And I said 0.48 on the previous slide, it's 0.3 here because I'm making a comparison here with the Hadamard bound itself. So we can always achieve something like a third of the Hadamard bound in any congruence class mod 4. And this is going to depend somewhat on what you're assuming is known about the distribution of primes, I guess. So the Hadamard bound is tight to within some factor, which is about a third, infinitely often. And this is what we know about how close we can approach the Hadamard bound in general, at least for real matrices. What I'd like to talk about now is lower bounds. So by that, what I mean is for every integer n, can I write down a matrix which is, has a large determinant, which is, somehow reasonably close to the Hadamard bound? The answer is going to be no. But, how close can we get? So this is an old theorem of Kohn from the 60s. Kohn says that you can do at least as well as like exponential decay. And remember that n to the n on 2 is a quite quickly growing function. It grows faster than the exponential. So, this thing at least is non-zero. And how do you do this? It's kind of, if you're used to doing Hadamard matrices, it's kind of the simplest thing that you can do. For technical reasons, Kohn doesn't want to worry about primes that are 1 or 3 mod 4. So Kohn just wants to write down a Paley type matrix. And this is what he does. This is his argument more or less verbatim. He says, choose the largest prime such that 2p plus 2 is less than n. Write down the corresponding Hadamard matrix. Fill it in with an identity matrix, to make it the right size, the size that you want to think about, n. And you compare the determinant of this matrix to n to the n on 2. And really, the only thing that this depends on is the gap between n and 2p on 2. So you see now precisely where gaps between primes are going to come in. The Kohn writing in the 60s knew that the gap between primes couldn't be as large as, n to the 2/3 or something like that. And that's basically where you see this minus 0.62 coming up. if you know more, if you assume more about the distribution of primes, you get a slightly better exponent up here. But if you used, the strongest thing that could possibly be true, if you assume that the gap between your primes is, on the order of the square of log n, you still only would get a constant factor here that looked like e to the minus log cubed n or something like that. So it would still grow faster than any polynomial, but slower than simply exponential. And that's what you can do with like this very, very simple thing. So there's another idea. Oh, that looks a little bit strange. Oops. I guess this is what happens when you like fix an error in your slides immediately before you go up to give your talk. So here's another idea. Carol mentioned earlier on the excess of a Hadamard matrix, and this comes into play here. So if I know that I have a Hadamard matrix in order n, can I do better than, what Cohen did in dimension n plus 1? And the answer is yes. The answer is that you do a Schur complement formula. So you look at your matrix M up here. So I guess A here is H, B, C, and D are just ones of the appropriate sizes, -1 maybe. And you can work out the determinant of the bordered matrix from the determinant of H. And it turns out what you're going to try and maximize, given that these guys are ones and -1s, is basically the sum of the entries of H. So in the case that you have a Hadamard matrix of maximal excess, the sum of all of the entries is going to be n root n. And it's a nice computation. It's not terribly hard to see. Did you get within a factor of like 0.61 of the Hadamard bound in the dimension n plus 1? And remember that we couldn't achieve the Hadamard bound in n plus 1 anyway, because it's 1 mod 4. So we would anyway have been aiming for like 87% of the Hadamard bound, but we've got 61%. It's not awful. So this idea was generalized by Richard Brent, Julian Osborne, and Warren Smith in a paper in the Australasian Journal of Combinatorics. And they did the following. They said, instead of adding a single row and a single column to my Hadamard matrix, suppose that I add whole submatrices. And here, like my naming scheme is R is selected uniformly at random, S is small, and D is deterministic. So what are you going to do? You're going to do exactly the same thing as you did before. You use the Schur complement formula, and you see that the determinant of this matrix as a whole is, well, as a factor, determinant of H, which is most of the matrix. And then you've got this other factor, S minus D times H inverse times R, but H is orthogonal, so that's not awful. And what are you going to do? R is random. We had to choose that to be random. You're going to choose D deterministically to maximize the determinant of this factor over here. So what you want to do is basically maximize the diagonal entries. You use some probability theory to show that all of the diagonal entries will be sized like root n minus D. All of the off-diagonal entries will be small, like big O of 1. And then you compute the determinant of that thing. And with high probability, you get a bound that looks like this. So to unpack it a little bit, so you have a Hadamard matrix of order n minus D. So you're packing on D extra randomly chosen columns and rows, or deterministically chosen rows, random columns. What you lose is a factor here, which is kind of exponential in D. And this number is like, it's less than 1, but it's not an awful lot less than 1. And you've got this factor over here that really only becomes an issue when D is on the order of square root of n. And that tells you that everything goes to 0 then. Right, so you really should think of this as n being reasonably large and D being, small, bounded by a constant or something like that. So if the Hadamard conjecture was true, the most that you'd ever have to do here is add on 3 additional rows and columns. And if you did that, you'd be able to achieve something like 1/10 of the Hadamard bound in all dimensions. That would be pretty okay. Unfortunately, we don't know anything like the Hadamard conjecture. We don't have anything near a dense enough family of Hadamard matrices to get this, but something can be done. So I want to tell you a little bit now about what happens in, well, the lower bounds. So really what we have is Cohen's bound from the 60s and the Brent Osborne Smith bound from like the 2010s. So this constant that I had before, whoops, that should be minus t there. So about a quarter to the minus t. And this bound is going to be sufficiently good, at least when t is at most the fourth root of the order or something like that. And as I say, conditional on the Hadamard conjecture, you would get a lower bound here of 0.1. So in contrast with the upper bounds that we talked about a few minutes ago, where we're all like conjecturally, pretty often within a constant of the best possible order, at least if you allow me to choose an order like, as a function of a prime, we get reasonably good bounds. In general, our lower bounds are basically exponentially bad. And, even with the strongest possible number theoretic conjectures in terms of the gaps between primes are going to grow. You're going to need to do something that's a little bit better than this. We get something that's still reasonably bad. So how much time do I have left?
Got 17 minutes.
Good. All right. So now that's really everything that's known about real Hadamard matrices, or the maximal determinant problem for real matrices. At least if you restrict yourself to plus minus one entries, you could say a little bit more if you allowed zeros in the matrix and things like that. Since we're in Kraków, I always think of Kraków as being the home of complex Hadamard matrices because of the database, right?
Shame, but thank you very much for mentioning that.
Yeah, so I want to talk a little bit about, well, at least a family of complex Hadamard matrices where I think this problem might be a little bit potentially easier. So I'm going to talk about Butson type matrices, and I'm going to restrict to the case that there are entries in the sixth roots of unity. And I'm going to show you that this already gives you some results that are quite hard for the plus minus one case, become a little bit easier here. And I will say that Guillermo is going to talk about third and fourth roots in his talk, which comes immediately after this, where also things are a little bit harder than they are in the sixth roots case. Yeah. So the first thing that I'll say is we should have some analog of the Hadamard non-existence results in the real case. So in the real case, you say if the dimension is odd, then I'm adding together ones and minus ones. I've got an odd number of terms. The inner product is never going to be zero. If you were working over pth roots of unity, you'd know that the only way that these things could vanish is if you had a complete sum of the pth roots. So you'd have to have the order of the matrix being a multiple of p. But I'm working over the sixth roots. So I've got plus and minus one in there as well as the third roots. I'm not going to get very many. I mean, I can always build two orthogonal rows, but I can still do something, right? So in the real case, you look at this number n to the n, which is the determinant of the Gram matrix. If n is odd and not a square, the square root of that thing won't be an integer. But I mean, I'm starting with the plus one minus one matrix and I'm trying to compute a determinant. That should be an integer. So the correct analog of that, the correct generalization here is to say that n to the n should be a norm in whatever ring of integers that I'm working in. And you do a little bit of algebraic number theory, and you see that in the case of z adjoin a third root of unity or z adjoin a sixth root of unity, what happens is the primes that are 2 mod 3 don't split. So I can't, if I see a prime that's 2 mod 3, which divides the square free part of the order, then that's not going to factor correctly. I won't be able to pull n to the n apart into two pieces of norm n to the n on 2. Okay, so I have no integer of the right size to be the determinant of my potential Hadamard matrix, so I'm dead in the water. Okay, so that tells me already that there's a list of orders. It's not as nicely behaved as in the real case, but there's a list of orders that I can't achieve. And it starts with numbers like 5, 11, and 15. 15 here is 3 times 5, but the square free part of the order is divisible by 5.
Let's say for size 15, there are no Butson type matrices of size 6, 15,6.
Exactly. So there's no Butson matrix with entries in the sixth roots.
Yes.
Also none with entries in the third roots, but this is a stronger statement. So all that I'm doing is I'm saying I throw away the square part, and if the square free part is divisible by a prime, which is 2 mod 3, I say there's no Butson matrix. Okay, I'll show you a table in a minute. This is the only restriction that we know. So it's not a congruence condition like in the real case, but it's not terrible for any size that we could hope to build. Well, we can factor in. So the other thing that I know is that these things exist definitely at Hadamard orders. This is why I want to work over the sixth roots and not over the third roots, because I can keep all the real Hadamard matrices. I should have said real Hadamard, I suppose. And also they exist at orders that look like 3 to the b. Why? Because I have Cayley tables of abelian groups of exponent 3, right? And tensor products of those things, everything is good. All right. So I want to show you a theorem that I discovered a long time ago in Ferentz's thesis, and then I lost, and then I was looking for a number of years, and then I found it. This is due to Ference and Rob. And it says the following. It says there exists a maximal determinant matrix of order n squared with entries in the 6th roots whenever, n is a perfect square. How does this work? Well, I'm going to remind you of the Paley core. So that's for any prime p, that's a p by p matrix, which is entries plus or minus 1 given by quadratic residues. In the prime case, it's circulant. In the general prime power case, it's like a multi-circulant thing. All that you need to know for the purposes of this talk is that p times p transpose is p minus 1 along the diagonal and minus 1 everywhere else. And it's got equally many 1s and minus 1s. So the row sums and the column sums are 0. Right? J is the all 1s matrix here. I should say that probably. And Rob and Ference say, look at this matrix H, which is p tensor p plus j tensor I plus omega squared times I tensor j, where omega squared is a third root of unity. And compute, I guess I should have said H conjugate transpose here, but H times H conjugate transpose, you do your sums. It's not awful. And what you see is basically everything canceled out, and this really is a Hadamard matrix. And I claim that the proof is really easy, right? It's just these 3 lines. And something similar is known in the real case. Well, you won't have Hadamard matrices of order p squared, but you might have Hadamard matrices of order 4p squared. And this is the subject of like 6 or 7 papers through the late 80s and early 90s, mostly by people like Jenny Seabury and her collaborators. And these are, these are known for most, but not all, like congruence classes of primes mod 16. I'm going to say there's 2 congruence classes that are not known, but I'll have to look it up. And the proofs are really quite hard. So I mean, typically, what are you doing? Instead of looking at quadratic residues that we did here, you're going to take p squared. You're going to look at like the p plus first residues inside of the field or something like this. You're going to group them together into like 16 cosets or something hard, and then put those things back together. It's a much more difficult theorem. So somehow, the idea, I mean, the motivation for this section of the talk is really this result, that over the 6th roots, some constructions are much easier. Some things are much easier to do than they are over the reals. And yeah, I should have convinced you of this, I hope. So I mean, how do I get from p squared to n squared? I just take Kronecker products, because Kronecker products of Paley matrices or Hadamard matrices are Hadamard. There we go. So we have existence of these guys. And then I just want to show you, I mean, I sat down. This didn't take me as long as I thought it would take me to draw. So I just went as far as order 60, and I tried to figure out when these things are known and when they're not known. And as I say, because my roots of unity are even, I have plus and minus 1 in there. So all of my Hadamard matrices exist. And what I filled in here are all of my non-existence criteria that came from earlier. So being divisible by a prime, which is, with the square free part being divisible by a prime, which is 2 mod 3. So you can see that that's not completely regular, and later on the pattern is going to be much less obvious than it is here. But at least if you're a prime which is, if you're an order which is 5 mod 6 or 11 mod 12, let's say 5 mod 12 or 11 mod 12, you will be divisible by at least 1 prime, which is 2 mod 3. So all of those orders are going to be ruled out. What was my notation? G means that I've got something there which is group developed. So really coming from an abelian group of exponent 6. White spot is about to be filled in next, right? So yeah, so I have Hadamard matrices. G means that I have something from a group, and N means no, nothing exists. And it turns out, so then I had to look for some computational results in the literature. And it turns out that the hard case is kind of primes that are 1 mod 3. So you can see the smallest open cases are, 37 and 43 are primes which are 1 mod 3. And I got one other sporadic case, but actually, 57 out of 60 cases are known, right? Existence or non-existence, which is way more than I was expecting when I started looking at this. So maybe the other thing that I'll say is there is no case, well, except maybe these 3 question marks, but there's no case as far as n equals 36 where non-existence occurs for a non-trivial reason, right? So the trivial reason being that the n to the n is not a square, is not a norm. That seems to be the only restriction, at least this far, but this is not very strong evidence on which to base a conjecture. So I'm not going to conjecture anything, but I will tell you what's in Ferentz's PhD thesis. Ferentz conjectures that the Hadamard bound will be achieved at all orders 2p, where p is a prime over the 6th roots.
So why means you prove that it exists, but the constructed proof, can you construct such a matrix for size, let's say 58?
Yeah. I don't know how to prove that these things exist without constructing them. But yeah. So this is what's known. And you can see that somehow the density of the set of orders as far as 60, where these things exist, is denser than the set of real matrices. But like for larger orders, asymptotically, I don't know what happens. But I would hope, given the like Soloshi-Cragen type construction, it's very tempting for me to conjecture that there are other short proofs that these things exist, which would be much, much harder to prove in the real case. So just to finish up, I'd like to talk a little bit again about more work of Rob's. And this is about the asymptotic existence of real Hadamard matrices, which I think was mentioned in his talk earlier. And he says that, I guess the precise statement here is not super important, but for every odd integer n, there exists a power of 2 such that there's a Hadamard matrix of order 2 to that power times n. And this is building on work of Jenny Seabury's that came before. And the game is kind of to optimize these constants alpha and beta that show up. Alpha grows slowly with n, but I'm really taking here 2 to the power of t, so you're getting really a kind of linear factor in n here, and then some constant beta. So Rob and his student Levinsky were able to reduce this constant here to a 5th or a 6th or something like that. And then you do a little bit of number theory and you work out what does that imply for the gap between Hadamard matrices on size n. What you do really is you look at what's the power of 2 that you have to add in to get from a Hadamard matrix at order n to a Hadamard matrix of order 2 to the t times n plus 2, this sort of a thing. And it's possible, but kind of hard to work with numerically or number theoretically, that there would be other orders in between there that would be the orders of Hadamard matrices. But you can at least prove something that's much, much stronger. So the gaps between the orders of Hadamard matrices grow like n to the 1/6, much stronger than anything that you could hope to say about the distribution of prime numbers, gaps between prime numbers, right? Even if you knew the Riemann hypothesis, the best exponent that you get here is like a half, right? So this theorem really is saying that the orders of Hadamard matrices are much denser than the orders of the primes, or prime powers, or whatever you would like. So if you take this result and you plug it into the Cohen type idea, so Cohen, remember, said, how do I produce a matrix with a large determinant of order n? Well, I take a Hadamard matrix that's close by, but not larger than that. Just fill it in with the identity. It won't make a difference to the asymptotics. And work with that. So if I use this bound here instead of Cohen's bound coming from prime numbers only, you get something like this. And again, I apologize, I should have an n on 2 here. And unfortunately, it's still an exponential kind of loss as I move away from the orders of Hadamard matrices. And now I can ask the same question for complex matrices. This is like my easiest theorem ever, because every real Hadamard matrix is going to be over the 6th roots as well. So we've got at least this many matrices over the 6th roots. I think that there are going to be much more, right? So you also have existence at every square order. You have all the tensor products of things that you know already together with squares. So we don't have very many obstructions at all. So it's hopeful that actually you could maybe even prove something like this, right? So it seems to me much more hopeful to prove that you can construct a sequence of orders, let's say with bounded gaps or something like that over the 6th roots than you could over the reals. So Compton, Cragen, and Delaunay in their paper on unreal Hadamard matrices suspect, they don't quite conjecture, but they suspect that this is the only obstruction, and otherwise these things are going to exist. It's a very interesting paper in which they show connections between matrices over the 6th roots and matrices over the reals as well. So sometimes you can get existence of real matrices from existence of well, what they call unreal matrices. So it seems to me that, potentially you could build denser families of these matrices. It's certainly a problem that's been much less well studied than in the real case. And I think it'd be an interesting thing to explore. So I have lots of questions. You've heard some of them, but here are a few more. You can take the probabilistic methods of Brent, Osborne, and Smith, and you can ask, first of all, whether they generalize to max det matrices instead of Hadamard matrices. They did use the Hadamard property a little bit in their proof, so they used that the inverse was the transpose. But I think that that's not an essential feature of the proof. But generalizing that is, not entirely trivial. Well, to get from, let's say, real matrices to matrices over the sixth roots. I think another reasonable question is whether the asymptotic methods of people like Rob and Jenny can be generalized from the real case to the sixth roots case. And I mean generalized in a less trivial way than the way that I did it, right? Which is to say that every real matrix is over the sixth roots. And can we do this with better constants that occur in the real case is the real question. And I mean, moving away just from purely Hadamard matrices to max det matrices, I think there are lots of interesting questions to ask there when Hadamard matrices don't exist, right? So there are various generalizations of Hadamard matrices. And here we're looking at the maximal determinant. But if you want to do something in applications, probably orthogonality is a more useful property than just maximizing the determinant, especially if you have matrices with orthogonal rows, not too many zeros that are close to the maximal determinant. I mean, so this is a question for the physicists. If a Hadamard matrix doesn't exist, what is the next best thing? What is, for applications, what properties should we be looking for? And, then once we know what we should be looking for, can we build them? How close can we get? And I want to pose this as a question, and it's whether there exists some constant bound for the Hadamard maximal determinant problem over the sixth roots. But given this talk 2 years ago, I would have just said minus 10 to the minus 2020. But now to make it a little bit harder, right? So, yeah. And dziękuję. That's all I have to say.